Hello everyone, and I am Manas Rai, and I'm going to give my video presentation on the topic uh, the grammar and Chomsky hierarchy in automata. So, grammar is basically defined by a quadruple where we have the sigma, v, and p, and a start symbol s. Sigma means the finite set of terminals. Vn means finite non-empty set of terminals. P means finite non-empty set of production rules. What is a production rule? Suppose we write that A alpha derives beta. So the production rule involves alpha belongs to sigma plus Vn clean closure, Vn sigma plus Vn clean closure. That is, we can have sigma or Vn. It is optional, and can have as many as and this asterisk can have any power. Any number of times it can be repeated. Okay, but at least one vn that is non-empty set of non-terminal should be there. It can have a leading any number of terminal or non-terminal and ending any number of non-terminal or terminal. And beta can be anything, terminal or non-terminal, but alpha has this vn. Next we have Chomsky hierarchy. Basically it defines how the languages are uh, defined on their type of restriction they pose on input. So this is sort of Chomsky hierarchy. Here we have this type 0 grammar, type 1 grammar, type 2 grammar, and type 3 grammar. And the language which accepts type 0 grammar is regular expression. And the machine on which regular expression is accepted is Turing machine. Similarly, we have type 1 grammar, which contains case sensitive language, and it is accepted by linear bound automata. And then we have a type 2 grammar, which is context free language, and it is derived by a PDA. It is accepted by a PDA. And the last, we have the most saturated one, which is type 3 grammar, and it is accepted by regular language. And if we can draw finite automata, then it is regular language. Here we can see the type 0 grammar. It has same for tuples. Alpha derives beta, and it is similar to normal grammar language. It can have any number of leading terminal, non-terminal, ending non-terminal, terminal, but one set of non-terminal should be there, and beta can be anything. Then we have further type 1 grammar, context sensitive grammar. Here the alpha is can have any number of terminal, non-terminal, uh, one set of non-empty, non-ending terminal, and ending terminal, non-terminal. But this beta, this is slight change. Here we have a terminal, non-terminal, but instead of clean closure, we have positive closure. That means here null is not accepted. Next, we have type 2 grammar. It is also known as context-free grammar. These are the four terminals. Here alpha is a set of non-terminal, and the length of alpha is 1. That is only one terminal, and that is non-terminal. Next, we have beta. It can be anything again, from terminal or non-terminal clean closure. Next, we have type 3 grammar or regular grammar. It is divided into two parts, left linear grammar and right linear grammar. Okay, then if alpha derives beta, A derives A or BA. Well, the left part is a non-terminal and ending is a terminal. And just opposite in right linear grammar, A derives A or AB, where the right or the ending part is non-terminal and one part is terminal. Part is terminal. Okay. Here is an example to just show it. S derives ASB and S derives AB. Now, we can have this S is a non-terminal and S can derive a terminal. So we can have any number of strings in by replacing S by ASB or AB. If we want to terminate it, just replace S by AB. And if we want any set of length, which is basically following A to the power n into B to the power n, we can use this. So that was all about the presentation.